Hello, I'm Adam Avison. I'm at the UK ARC node in Manchester, and I'm going to be presenting the Observation Support Tool, the OST for short. Okay, so let's see. It's just a quick overview of what I'll be discussing today. So I'll introduce the OST, give you a bit of its history, explain how it works as a tool you will interact with, and then we'll go through the OST website, and then we'll end with a few guided demonstrations. Hopefully we'll fit them all within the hour. If we're running out of time, then I'll drop one of them. But at the back of these notes, there are all the parameters for the demonstrations that I will use. Okay, so here we are. What is the ALMA Observation Support Tool? It is an online ALMA simulator, which is aimed primarily at the non-interferometry expert. So if you are new to interferometry or new to ALMA and you do not have the time or do not want to learn how to use more sophisticated or more demanding tools for simulating your ALMA observations, then that's what the OST is primarily for. It has, since its inception, evolved slightly beyond that, and I'll discuss that in a couple of slides time. So in essence, the OST is a web form that you can fill in. You put in some observing and imaging parameters, and then you give us an email address and you click submit, and we process your simulation for you in Manchester. And this is just a glimpse of what the OST web form looks like, but we'll see it again as we go through. And of course, very important, this is the URL that you need to navigate to find the OST. Okay, so why simulate? Well, there's a couple of key reasons. The OST initially was developed as an observation support tool, as its name, which is to help with proposal preparation primarily. So if you have a set of observations that you want to make with ALMA, and you have a model or an observational analog of the source that you want to look at, so either a model you've generated yourself, or say some far infrared or near infrared actual observation that you can use as a sky model, you can go to the OST and test the observing setup that you want to use for your proposal. This is particularly important if you're moving from a single dish observation to an interferometric observation, because those things behave very differently. There are effects of missing spacings, and you can run into surface brightness issues. So the first of those being because an interferometer does not have an infinite amount of baselines. There are gaps in its spatial scale coverage, so it acts as a spatial filter. So depending on the baselines available in your interferometer, you will be missing information on spatial scales. Particularly for ALMA, that usually is most obvious in the missing zero spacings. So you don't have baselines of zero length, so you are missing essentially total power if you just have ALMA array data. Of course, ALMA provides total power observations as well, but if you cannot justify those, then you may need to work on that. And then the other point being surface brightness sensitivity issues. So if you're familiar with an object through single dish observations, and you know its flux very well, but it's not resolved or very marginally resolved in your single dish observation, as you start to resolve it, the surface brightness will be split across multiple beams with your ALMA observation, which means that you will have to consider more sensitive observations to get an equivalent signal to noise to your single dish. observation. So that is sort of things you can do in testing for during your proposal preparation to make sure you're going to get something useful out. The other thing is then you can use these simulated images as evidence in your ALMA proposal to say, we have this model, this is what we believe we're going to receive, should you give us ALMA time, and justify your observational setup that way. The second a good reason to simulate is once you have data, whether you've got your own ALMA time or you found something in the archive that you are working with, if you have a model that you believe explains the observations, the emission in your observations, then you can simulate to compare your model as corrupted by the interferometric properties, so the array configuration and effects of timing and weather on your model to create a more realistic simulated observation, which you can then compare directly with your data and see how well your model holds up. So those are two good reasons to simulate, and the OST has functionality that will let you do both. Okay, so a brief history of the OST. It became available on the 28th of March in 2011. So we're nearly 10 years old. Party poppers and party hats, woohoo. So since then, it has processed over 26,000 simulations for users around the world. So the last time I counted, which was earlier this month, it was 42 unique countries, which is kind of cool. And just so you're aware, we generally create a new version each year to coincide with the ALMA call for proposals, and typically every other year. So for odd numbered cycles, we have historically introduced a new larger capability. So some of them are listed here. We introduced data cubes in cycle 3 and the ability to handle Stokes cubes in cycle 5. So yeah, that's the OST. I should also credit here up until sort of the end of March and March 2011 and a few months thereafter, the OST was initially developed and looked after in part by Ian Haywood. But since that time, I have been the primary manager, upgrader, coder of the OST. But credit to Ian for getting it started. Okay, and just so you can see how these 26,000 simulations, what they look like, this is a bit of a busy plot, but this is every single of those 26,000 simulations plotted on one plot. So every single day by the blue line, and their 7-day running average. And you can see we have busy times and quiet times. The green and red lines show the start and end of call for proposals. So we get busy during those call for proposals. But then we're not quiet the rest of the time. People do use this for other things. Okay, so how does the OST work in practice? Here's sort of the nice simplified flowchart of what goes on. So down the page, hopefully you can see my mouse. Down the page we have time, and then we can follow what happens with a simulation as it goes through. I should probably point out here that I'm going to use the word simulation and job when in reference to a simulation occurring on the OST interchangeably. Job is just shorter, and it's what I typically tend to refer them as. So if I start mixing them up, they both mean the same thing. Okay, so for a simulation to start, we need a user to go to the website and fill in the web form. The web form, with this little side note over here, contains a lot of in-browser checks. So for each, or for the majority of input parameters, there's a little bit of JavaScript, which checks things like, is this the right format? Is it a value that's allowed by ALMA? And if that, if any of those are false, so you've entered something that won't work, then the OST will not let you submit the job. So it should also give you a little explanation as to why your input is wrong, to help you to correct it. So once you've got a web form that the OST is happy with, then you will submit it, and then at that point the OST will join. The job will join the OST's queue. So it is a queue-based system, and I'll discuss that a bit further in the following slide. So at some time later, your job will move to the front of the queue and pre-processing checks will start. This is another round of checks done within the main code of the OST, which checks things that weren't checked on the web form, checking whether the data that is being submitted is of the right format and things like that, whether you've submitted realistic numbers that might have got past the in-browser checks. If any of those do not pass, then you will receive an email notification saying that there has been a problem and explaining that problem. But hopefully that won't happen. You will pass your pre-processing checks and the simulation will start. The simulation then runs through all the bits and pieces of taking your input parameters and the model that you want to use, creating a measurement set, and then imaging that measurement set so that we can feed you back the images for your simulation. Here, there are two scenarios. The most likely is that everything will be fine and you will receive an email, a second email, a third email, second email, saying here your simulation is complete. Here is a link to where your simulation output is. On very rare occasions, the simulation fails, and that is usually because something that has passed the in-browser checks and passed the pre-processing checks has caused a problem, and the main cause for this is FITS file images that have been uploaded that the OST can't handle. So the FITS format is a standard format, but it has many extensions and parameters that you can include or not include, and some of them the CASA backend of the OST can't handle, and that causes a problem. In those cases, the OST will crash. Software we have running monitoring the system will email the OST admin, so me, to tell me that there is a problem, or whoever's looking after it at the time there is a problem. It will then move the failed job, so your job, out of the queue, so that and then it will restart itself, so the OST will start running again. We move your job out of the queue so that the next job in line can proceed, so no, people aren't left waiting, because typically this happens at 2:30 in the morning UK time, so I'm not going to get to the office for several hours to fix this. And if this happens, what typically, well, as soon as I get into a position to check my email the following day, or that day if it occurs during working hours, I will investigate, I will find out what the problem is and email you as a user to explain how to fix it. Okay, cool. So that's the scenes of what goes on after you click submit on the web form. Just to comment on the queue. So as I said, the OST is a queue-based system. So people can submit jobs at any time, but the OST can only submit one job at once. So can only process one job at once. So it will your job will wait until its turn in the queue before processing starts. The exception to that being when it is a very busy time, so the last 4 or 5 days before a call for proposal deadline, we turn on the OST overflow, which is a second system which will run jobs. So it will take any job after X in the queue, move them to a different system and start processing them there, just to make that queue, both queues, shorter and jobs get processed more rapidly. The 2 plots at the bottom just give you a bit of an indication of what the actual processing times and what we call return times are for jobs within the OST. So the return time is the time from a user clicking submit until the email saying that their job has been completed is sent. And typically those are, let's see, I made some notes. Yes, so 94-ish% are returned within 15 minutes and 97% are returned within 25 minutes. But as you can see from the plot here, this tends to be much lower values than either of those. On the rare occasions, there's a really large value in here. That's where something has crashed and it's had to wait for me to go and fix something. In terms of processing, when your job has got to the start of the queue, this usually happens really quick. So this peaks at around 1.5 minutes, and most things are done in less than 15 minutes. So when you're at the front of your queue, things are pretty quick. But it's just worth bearing in mind that there may be a queue, so don't try and do a simulation 30 seconds before the deadline. It's not going to be returned in time, I'm afraid. Okay, so a bit more behind the scenes. This is sort of the technical stuff. The OST in its current version, which is 8.5, runs in CASA 5.6.2-2. The code that runs the OST to make the simulations uses the CASA simulator toolkit, the SM toolkit, not SimObserve, which is the CASA task, which is created for simulating observations. As they are not running the same, your results, of course, will be slightly different. And simulated measurement sets, which are the data sets within CASA, are imaged using the cleaning task of CASA. This third bullet point here is an important one. Images are output to the user. We do not retain measurement sets. They're too big to store the amount of traffic we tend to get. So it's just images. And the fourth is also important. Everything relating to your simulation. So if you upload an image, all your web form input parameters, including your email address, and all the outputs are deleted at 2 minutes before midnight, 2 days after your submission. So, for example, if you submitted something at either 9 AM or 9 PM on the 1st of March, at 11:58 on the 3rd of March, everything to do with your job will have been deleted from the system. So make sure you take your outputs away with you when you get them. This is just to keep the system as tidy as possible, especially on days where we have 200, 300 submissions. Our storage capacity starts to get a bit squeezed. Okay, and while we're talking about things you need to bear in mind, there are some other minor limitations on what you can do with the OST. They are that if you choose to upload a FITS image, you are limited to a size of 10 megabytes. And output images for continuum images are limited to 2048 by 2048 pixels. If you image a data cube, then in terms of the the spatial X and Y scale, you have it limited to 512 by 512 pixels. So if your simulation generates a image that has a cell size, which means that your area of sky that you're imaging is bigger than these cutoffs, it just truncates the FIS file and won't image beyond there. And again, these are enforced to ensure sufficient disk space for all users. Okay, and finally, another set of things to bear in mind before we start looking at the website. So the OST generates accurate simulations, but we can't promise to match exactly real data. Things that are kind of difficult to allow for or correct for in a simulation are things like scan spacing. So in your actual ALMA observations, you'll have scans on a phase calibrator, then on your source, back to phase calibrator on a source, until you've got enough on source time. To get that scan spacing can be tricky, although there are options within the OST that do allow you to input some of that off source time into your simulation. Another thing is the elevation of your object during a simulation might be different. That is because in practice, the OST is, all OST simulated observations take place on the same day. So the rise and set times of your objects may be different to your actual observation. And of course, in the real world, the weather changes on a second by second basis, whereas during the simulation, you are fixed at a given atmospheric corruption factor, which we'll see later on. So there's a handful of things to bear in mind when you come to use the OST. Okay, cool. Next slide. So let's start looking around the OST website. So when you navigate to the web address at the beginning of this presentation, so alma-ost.jb.man.ac.uk, at the top of the website, you will see the header and then the navigation bar. So I'm just going to discuss where all of these things go. So of course, the first one is the OST. You will go to the OST web form. Next, we have a news page, which has things with updates. So usually pointing out that the call for proposals is coming, or we upgraded the system. Occasionally, unfortunately, if there's been a problem, so the Jodrell Bank network has gone down, so the OST was offline for a while, we will point out that has happened, and general OST related news. Help takes you to a very long and detailed set of documentation explaining all of the input parameters and their behavior for the OST web form, which I encourage people to look at when they come to use things, if they're looking for more complex simulations. Excuse me. Okay. So just as an example, here is some of the OST news page from nearly a year ago now, explaining that the call for proposals for cycle 8 was postponed. And these are the kind of news articles we will put up. In fact, on the web form, you'll see that we have, when we come to the live demo at the end, you'll see that there's a little news link that highlights important news that I've put up at the moment. And then the OST help documentation. So this is just a snippet of all the parameters and all the files within the, not files, the subsections within the help documentation that you can navigate to. I'm going to highlight and emphasize this one. there's a section on information relating to FITS files, and this one highlighted here is the most important bit. As I was saying, that the thing that causes the OST to crash the most is FITS files that the OST cannot handle, and usually the answer to a crash is in this section of the documentation. So if you, before you submit a FITS file, if you've made it yourself, just check that you've fulfilled all the criteria here. Okay, cool. Back to this navigation then. We have a button that says queue. So this will take you to a link which will show you a live, at the moment that you click it, status of the queue in terms of the number of jobs that currently exist. So if you're not too fussed about waiting, then if you see a large number, then you can submit a job. If you wanted some quick answer, then you could go away and wait until the queue had died down and then submit it. It's just good to know that if you're waiting for a while, if your emails aren't coming back, then perhaps there's a reason in a long queue. Next, we have a link to the image library. So during the demonstrations, we're going to use images that are part of the OST library. So this is a selection of images of astronomical objects that you can use for your simulations, just to get a feel for the OST before you start submitting your own FITS file. And finally, there's a link to the acknowledgement. So the proper reference if you use the OST in a published work. So if you do use it for simulating models, comparing your models to real data. Of course, for call for proposals and proposal preparation, you don't really need that. And finally, there is a link to ALMA Help Desk should you want to submit a help desk ticket relating to the OST. We get surprisingly few of those. I think that's usually because if a job gets stuck, I tend to have emailed the user before they think to get to the help desk, unless something has gone really spectacularly wrong. Okay, so just another couple of quick looks. So this is the a snapshot of the library page. So you can see we've got models of model protostellar clusters, something that's a bit like NGC 1333, but rescaled, and there's a whole bunch of other sources in there. There are some extragalactic objects as well. Okay, right. Now we shall go through what's actually on the web form, so we can start to get a feel for what's there before we get onto the hands-on demos. So this is the web form again. We saw it on the front page. So it's sectioned up into different parts of the simulation setup. So first off, we have the array setup. So this is selecting the ALMA configuration that you want to use. We have, this is a drop-down menu. We have a whole bunch of options, those being the nominal configurations that get released with each call for proposals, going back from cycle 8, which is the current one, all the way back down to cycle 0. And they have some specifics that tells you the maximum baseline and things like that. And then also we have at the top, we have user upload option. And if you click that, then below this instrument, a little drop down will pop up and allow you to upload your own configuration file if you have it in the right format, which is specified by the help. And then we have these three sort of generic cases, ALMA, ACA, and ALMA plus ACA. In these cases, one of 28 inbuilt CASA configurations will be used for, this is specifically for ALMA or ALMA plus ACA, based entirely on the user requested resolution, which is a parameter further down the web form. So we can select which array we want, and then next we want to go and set up the sky. So this is what we're pointing at. We have source model, so you can choose something from the library. Again, this is a drop down, or there is the other option of user upload. If you select that, then this box becomes ungray, and you can click choose file and go and find your file on your system and submit that. Then we have declination. So what is the declination of your observation? This is a very picky parameter. You have to have the formatting of this just as the OST likes it, otherwise it won't let you submit the web form. And then you can rescale your image. So this will take the maximum pixel in your image and scale it to whatever value is given here. So you have the units, Janskis, millijanskis, etc. that you can select. So let's rescale the maximum pixel in your image to this value, and then every other pixel relative to that. If you leave it at 0, then it will use whatever value is in your original image. Okay. Then we have the observing setup. There's a lot to go through here, and I will discuss it during the live demos, but the main ones to note are whether you are doing a continuum or a spectral observation. That will change these parameters here. Your central frequency and bandwidth, these are typical parameters, but are observing mode specific. We'll see that in the demos. This required resolution is the one that I mentioned before, which comes into play if you select ALMA or ALMA plus ACA. And then you have pointing strategy, time on source, start hour angle. So this is the time relative to your source going through the zenith. And number of visits is how many times that observation is repeated. So that means this is basically scales the noise. So if you put multiples, values greater than 1, and they have to be integer values, then it rescales the noise as if it had done the same observation over and over again X number of times. And then finally, include cycle interface calibrator. This is the option that allows you to put in gaps within your observing time as if it was a real observation going to a phase calibrator. Okay, right. A kind of important one here is your atmospheric eruption. So at ALMA, at millimeter wavelengths, then your atmosphere is important. We corrupt the noise in your observation. We corrupt your observations based on the atmospheric properties you request. So we do that by taking your observing frequency and one of the 7 octiles measured, 7 octiles of precipitable water vapor, which is used by the observatory itself when scheduling observations. So we take the weather conditions of each of those. So in this plot, you can see 3 of those as good weather in red, sort of relatively good weather in purple, and slightly worse weather in blue. So you can see at the higher ALMA bands, higher frequencies, the atmospheric transmission really starts to drop off. We take our atmospheric transmission and convert that into a sky temperature, combining that with a receiver temperature. We get a system temperature, and we feed that into this is the RMS visibility noise within the simulation. So your bandwidth and time on source and properties of the antennas are included there. For a bit more information on the 7 octiles and how they are chosen, I refer you to this section of the ALMA technical handbook, which goes into it in great detail. Okay. And then imaging setup. This is what you want back from your simulation. So weighting, is a parameter of clean algorithms. So you can choose between natural, uniform, and Briggs. Natural will give you better signal to noise but lower resolution. Uniform, poorer signal to noise but better resolution, and your Briggs will be somewhere in between. And we fix. I'm not going to go into too much detail on weighting here, but we fix the robust parameter at 0.5. So that means that it is a bit more like natural weighting than uniform weighting. So you'll have slightly poorer signal to noise than natural, but a slightly better beam, higher resolution than you would in natural weighting. And this is in line with typical ALMA pipeline imaging behavior. Weighting your images is a topic in of itself, so I refer you to the documentation. This is quite a useful little guide within the CASA docs, the link at the bottom here. And the other two options here in the imaging product section of the web form are, do you want to perform deconvolution? So do you want to actually clean your image, which means remove the artifacts from your synthesized beam? Yes or no. It defaults to no, but most people would actually want a clean image because that's the kind of data you'll be working with science. And then your output image format, you have the option between a FITS file and a CASA image. If you select the CASA image, then because CASA images are a directory structure, it just creates a tar file and sends you that. And last but not least, we need an email address from you so we can first let you know that your submission has been sent to the queue successfully, and then either let you know if something's gone wrong or let you know that your simulation has failed. We keep this for up to 48 hours, as I said earlier, and if you are interested as to how we use and how we store your email address, then there is a privacy statement just next to the submit button. Okay, right. But yes, as it says, your email address is essential. If you don't submit one of those, then nothing will happen. You're of course free to put in a fake email address. It's just then up to you to make sure you find your simulation. And if something goes wrong, you may never know. Right, okay, cool. So we are now at the point where we can start to go into the into the guided demonstrations. I will just flip forward one slide to show you that at the end of the presentation, there are the input parameters for all of the demonstrations that I intend to do or intended to do. Okay, you should now be seeing my copy of Google Chrome with the OST webpage loaded. So just to point out, this pinky red bar was the link to a news item, and that was just because we migrated the OST and upgraded it a couple of weeks ago, thankfully in time for this presentation. Okay, so let's go through a demonstration of setting up a very simple OST simulation. So first, we're going to use the simplest option. We're going to select just the ALMA configuration. Just as this is being recorded, I will also just quickly click that, and you'll see that the option to upload a configuration file exists, but we'll go back to ALMA there. We've got the options for all the library images and upload fits, which ungrays that box. But we're going to stick with central point source, just because I'm going to keep looking off screen. I also have the last slide of the thing printed out, which is what I'm referring to. Okay, and we're going to select 40, declination of 40, just so it's not the default. And we can see that this live validation has said that my input is okay. So if you do select the point source, you need to put something in the image peak. Otherwise, you will just get a blank field of noise. So I'm going to put 0.5 millijansky. We're going to use continuum image, continuum observing mode. The other option is spectral, which changes some of the parameters. And I will show for the video some of the changes that can happen, and we will see in the following demonstrations. But if you change the bandwidth to 32 gigahertz, which is not possible by ALMA, then you see that it gives you the option use recommended continuum setup, yes or no. It will then, if you say yes, it will limit your observation to 7.5 gigahertz, which is the maximum, and it will detect what observing band you're in, and pick the recommended continuum setup for that band, given the 7.5 gigahertz coverage. But we don't want to do that. So what if we put something like 2.2 in? Then you get a different set of options. The OST allows you to specify up to 4 spectral windows in of 4 different bandwidths, as long as they add up to this value here. And it will ungray boxes depending on how much bandwidth you give it. If we go to 5 point something, then you see the third option, and then if I went to 6.8, then all of them are available. But in this scenario, we just want 0.5 gigahertz, so that will get rid of that thing. And we want to do this observation at 230 gigahertz, which is band 6. I'm going to leave the number of polarizations as they are. You do have the option to upload Stokes cubes. If you leave this option as no, then it will just do Stokes I, so total intensity. If you select yes and have submitted a Stokes cube, then it will perform simulated images of each of those, each of your Stokes axis. If you click yes, but your FITS file is just total intensity, then it will just do total intensity. Okay, right. So as we selected ALMA at the top, when we come to required resolution, we can actually put something in here. This will now select the nearest inbuilt CASA ALMA observation configuration file that will give a required resolution of 0.2 arcseconds at a observing frequency of 230 gigahertz. Right, next, our on-source time, let's make that 2 hours, and we will start an hour before, so an hour before the object reaches its zenith. Negative numbers are before, positive are after, and we're just going to visit once. Include cycle interface calibrator. This is the option I've mentioned, which allows you to insert pauses in your on-source time. For the purposes of the recording, I'm just going to show what it looks like. So you can say, I want to go to a phase calibrator every X number of seconds, as long as that X is between 5 and 10 minutes. And I want to spend Y seconds on the phase calibrator, again, as long as those are between 30 and 120 seconds, which are sort of reasonable ALMA values. But in this case, I'm going to leave that as no. We're in band 6, so we can have not the best, but reasonable weather conditions. So I'm selecting the 3rd octile. I will leave the weighting as natural. Yes, we do want to perform deconvolution, and then we'll give it my email address, which we'll give it my work email address. So you'll see in a couple of instances that the OK has popped up. That's because we changed something dramatically. If something has gone wrong, then we will know now. If not, it will show you this page. So this is a quick, so this is a submission page that you get. It tells you things like your result will appear here. So this is the name of your job, which is the year, the month, the day, the time, hour, minute, seconds, and then a string of 5 characters. I once, a long time ago, demoed this at ESO in a room full of astronomers, and everyone clicked to submit at the same time, which meant that whoever clicked submit at the last millisecond or whenever the time ticked over actually got this job, which is why I add these 5 random characters to the end to avoid that. It also tells you that you're in the queue and there is 1 job in front of it. So someone's already using this, and you will receive further notifications via email. Okay, so we'll just nip to my email, and you'll see this is the kind of email you get. So your request has been submitted and you'll be notified when it is complete. You can also then click on this link and it says simulation in progress. So that means in the time I have taken to talk and show you my emails, my job has moved from the queue into being processed. If it wasn't, it would say job in the queue. Okay, so that's all we really need to do with the demonstration. Actually, no, what I should show you is the output. And I can't see the attendee list, so I don't know how many people who would be familiar with the British TV show Blue Peter, but here's one I made earlier. Okay, so this is the same simulation that I've just processed, but I did it yesterday. Okay, so this is your output page. It will actually just be your timestamp .html at our web address /output. So it tells me that the configuration ALMA out 15 has been used, and a lot of the input parameters. Then it shows you a PNG of your simulated image, which is this one. It also, go back. Each image has what's called a histogram equalization image next to it, which flattens off the histogram of the image to show you what's sort of the noise in the background. So that's our point source, our simulated image. We can download our FITS file here, so save link as. Then we can see the dirty beam and the equalized version of that. And we get a look at the UV coverage, so it's really good, nice and round because we had it at zenith and declination is nearly above ALMA. We can look at the atmospheric transmission where we were. So this is covering all bands of ALMA. And this is zooming in closer to where we actually were. And then elevation versus time plot. So an hour before and an hour after, because we had 2 hours on source. And then finally, a little diagnostic saying it took 60 seconds to process.